All of you are able to open the quiz?
The quiz is the checkpoint, module 1 checkpoint.
Module 1 checkpoints. The questions are very simple, just to make sure that we are all good before we move on. I need it. I am around, so feel free to ask me questions too, okay? No, the Wi-Fi. I'm using the C5 camera. And play the YouTube. You know, I think there is another one, another method. Password is 8791. 8791. Yes. Yeah. What are the differences? So, for example, the softmax, okay, it's not traditionally used within hidden layers. Why is that? Because softmax is outputting values between 0 and 1, and anything between those. So these are actually probability values. The softmax activation function is used for the final layer, which is going to make your prediction. So once you want to actually get the probability value out, then this is what you're using. The sigmoid, the RLU, and the linear regression are most likely similar, but there are now technical issues when you are going to train. Remember back propagation and probability. So when you are doing so, there is something in your whenever you come to algebra, there is something called vanishing or exploding gradients. So that means actually that while training, actually some of the also becomes zero. Okay, and this is actually where those are become points. So changing or playing with one versus the other, actually you can eliminate this issue. You can eliminate the issue of losing this information within the units of the layers. technically this is why. Remember in one of the slides, relative it's popular, and once it was proposed, it was very useful for the vanishing problem, for the problem of information frequency. Simply because it gets the maximum in 0 and anything else. Other ones, they can saturate value 0. Okay, so for example, the case one, hyperbolic function, can give you outputs that are very close to the response. And this will support the new okay. So for large networks, and because you don't want to actually end up with the fancy puzzle, you use the relative in the hidden layers. Yeah, that's fine. Yeah, maybe yes. You are? Resnet, you said? Okay. Okay, yeah.
Introduce the introduce the
It takes the input and output just to the output training, so it makes a skip connection.
Okay.
So this is the way that
Tragošim predopizime matematike do višjem
The overview, not the balance.
To je čo diskurs.
The rest.
Osnovno išao na tom projektu.
And I guess we're talking about the preprint model.
Kam razvija i njom.
So this
Questo
actually
funzione relativista tiješta. Funkcioneš linearno, da je proboriješ. To funzione per
some already trained ways from an application that have used millions of training and you adapt it to your model. So your model becomes more powerful. So this is actually very good to avoid overfitting. Not the The vanishing problem is actually a problem that is related to
Imaš prijemljeni
back propagation
i sklapanje funkciona aktiviziranje.
It's more related to theoretical. Because it happens plainly when you are doing ratings and you are doing back propagation. So, for instance, a couple of techniques that have been proposed is changing the output. So remember that I always integrating the signal to, so there is something that's called stochastic, there is something that's called momentum. So these are actually different strategies that you can use in order to bypass that. Initialization is another way to bypass Yes. Who left? Yeah. All right, shall we discuss it together? So, any questions? Okay. Which statement best describes the relationship between AI, machine learning, and deep learning? Third, deep learning is a subset of machine learning, which is a subset of AI, right? So we discussed this at the very first slide, if I remember correct. Jeka mentioned. No comments on this, so we can go to the next one. What is the main purpose of a neural network? Right. So, to store large data sets? No. To manually define rules for predictions? No. By the way, the second one is something that AI does. Okay? So AI is a field. It's a discipline, which actually you can do in order to predefine rules or find sophisticated ways to define rules in order to make predictions. Learn patterns from data and make predictions? Yes. Replace GPUs? No. GPUs are actually part of deep learning. What do weights represent in a neural network? Second one. Right? Right? Adjustable parameters that control how input data is transformed. Right? So we start with initial features about the data, we feed it in, then parameters W1 through blah blah are getting there, they transform, they take you to the second layer, they transform the input data, they transform the features to other type of features, then you go to the next layer until you go and make predictions. Okay? Why are activation functions important in deep learning? Second, very good. They introduce the nonlinearity into the model. Okay? You all know that, so I don't have to go through this. Okay, now this is interesting. We haven't covered that much. You make that's fine. Which activation function is commonly used in hidden layers of deep neural networks? What did you answer?
Yes, I choose sigmoid, but it was really.
Okay, sigmoid. Okay. Yeah, so most common. So this is actually a tricky question. I mean, it's fine if you don't get it correct. We said previously that the ReLU activation function is one also that eliminates the issue of vanishing gradients, right? So when we do optimization, when we are doing gradient descent, a lot of information or a lot of neurons, they receive, or a lot of parameters, they become zero as you go deep to the network, as you move forward until your prediction, your final prediction. Okay, so this is actually called the vanishing problem. And it is directly linked with optimization and the choice of the activation function. If the choice of the activation function makes the values saturating at zero, then most likely the deeper you go, the more zeros you will out. That means that the information is lost, that means that you destroy your features, that means that your final prediction is going to be wrong. Okay? Softmax. I'm going to comment on the softmax because I think it's important. You got this one? Okay. Softmax, why it's not? Softmax is an activation function that is outputting values between 0 and 1. Real numbers, anything between those two numbers, between 0 and 1. Okay? So it's perfect if you want to actually get predictions based on probability values. Okay? So it's ideal for the final layer, the layer that makes the prediction. Alright? So the layer that will tell you eventually that the digit number 2 will receive a probability value of 0.9, recognizing that the 0.9, recognizing that this is the digit number 2. Alright? So again, its probability values is ideal for the final last layer. Okay, I answered this. What does the loss function measure? Right. It's easy to get this correct, but this is actually the point of the whole lecture today. So backpropagation, gradient descent, Remember, Gerda mentioned difference. So in the video, you saw that you have the value 0.2 and 1. 1 is actually probability of 1, and 0.2 is the predicted probability, right? And what did the people do? They said, okay, now we're going to measure the difference. How? 0.2 minus 1, square it, right? And this is actually plus all the other square differences, and this is actually my loss function. Yes? No. We talked about high school and then optimizing, minimizing a function, right? So we said in high school we were saying f of w equal to w squared, and this is like the parabola, right? And then the minimum gets at 0.0. Now, that's exactly what is happening here. The loss function is your cost function that we are trying to minimize. And it's actually defined as the sum of y minus y hat squared. Okay, where are the parameters? The parameters are inside the y. Y is a function of the parameters. Right? Remember that y is actually a linear transformation of x1 times w1 plus x2 times w2, blah, 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 plus xn times wn. And then you apply also an activation function on it. Alright? So now this is actually your cost function that you are trying to minimize. And because it's so complicated, you are seeing such weird hypersurfaces in a high-dimensional space. Okay? And then this is where gradient descent actually becomes popular, because it will enable you to actually start from one point on that surface and go and move at the minimum, or what we call at the local minimum, because you will never reach the global minimum. Good?
Do you have an idea why it is squared?
It is the distance
It makes the mathematics simple.
It is the distance between the target and the
Yeah, but
computer.
why squared?
Square.
Why
Distance square.
To avoid positive and negative values.
It's
It makes
the
the
same
math
that
simple.
we have in regression, let's say, if we think about
But
statistics.
you can also think as the distance in
Yeah.
multi what's
The
it?
square of the distance, yes. The square of the distance.
Multi-dimensional
It has a geometric
space.
interpretation.
Yes.
Very good. So everything, by the way, this starts from a linear regression, right? So that's what we are measuring also in linear regression. In linear regression, the difference between neural networks is that it has only one layer, plus it doesn't ever apply an activation function on it. So in linear regression, what you have is y is equal to x1 times w1 plus x2 times w2, blah. Now, in neural networks, you generalize this. You have, within a layer, you have multiple of those equations, and then you also have many layers. So you could imagine now how many parameters you need to estimate. Good? Good. Backpropagation primarily used for updating network weights based on prediction errors. Yep. Why is normalization important when training neural networks on image data? This we haven't covered yet. We're going to cover soon. It's C, the third. Okay, so it helps stabilize and improve model training. So we will see that when we're going to work with the MNIST dataset, the initial features are values between 0 and 255. Okay, so you would imagine now that the distance between the value 0 and 255 is far away, and anything in between will scale up as you are moving forwards to the network. Okay, so what we want is to normalize this and make all the values between 0 and 255 between 0 and 1. Okay, so 0 and 1 now has a smaller distance. So that will help us with the gradient descent, and it won't actually, and it will actually enable you to estimate the parameters properly. What is one major advantage of deep neural networks over solid models? Second, yeah, they can automatically learn complex hierarchical representations. Second, yes, very good. Now, one, I really liked what Gerta mentioned before about we are adding the layers, and then she had a very nice visualization about how going from one layer and to the next layer actually it makes you those decision boundaries to be nicely squared, circles and stuff like this, remember? So I want to make a historical point here. When neural networks started like 1950s or whatever it was, back then, they actually started with something called perceptron. Very basic stuff, okay? Very powerful. Then people realized that we cannot actually separate complicated data. So they figured out, like in the 70s, 80s, 90s, that okay, the way to separate those types of data is to actually add nonlinearities, increase the number of layers, and so on. However, there was one limitation, and this is what made, back then, in the 90s, neural networks unpopular. Hardware. We didn't have computational power back then, exactly.
Because we need a lot of data to train the network.
We didn't have, I mean, we could get a lot of data, but also the lack of a lot of data, we couldn't actually make those models powerful. Hardware was really important. We couldn't actually train, it was taking forever. That's why, back then, 1990s, something called support vector machines came up. And they were actually pretty good, pretty efficient, mathematically stable. They had even closed form solutions and so on. And it was, for many years, that was actually the state of the art. 2000 plus, hardware actually came. How? The gaming industry actually introduced GPUs. Okay? And then this is how we started this evolution, and here we are today. Okay? Good. And we don't know where to go.
And computer architecture.
And computer architecture and better mathematical tools and blah, 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 all of this good stuff that came out. Okay? Good. Any questions? All right. Okay, now we're going to go to the this computational aspects, and we're going to actually get into the code. Though I'm not going to code anything because I have everything done, but feel free to open also your notebook if you want and see the analogy between what you see here and what you have on your notebook. So, what we're going to work on? We're going to work on a classification problem. It's a supervised task. The goal is that we have handwritten digits in a form of small images, okay? And each of those digits over there that you see on the screen is coming with a label. So if you see a handwritten digit 0, that means that it has the correct label 0. Okay, so this is actually a massive data set. It's a benchmark data set, contains thousands of handwritten digits. It came up by LeCun, one of the fathers of neural networks. Okay, he got also the Turing Award back in 17, I don't remember, 17, among with other colleagues. And the goal is that I would like to train a neural network with those digits in order to predict the correct label of an unseen data point that looks like that. So if I train my network properly and then I take a random image, handwritten digit 28 by 28, and I give it to my network, the network should predict the correct label. Okay? Is it clear the task? Okay. The data set again, it's called the MNIST data set. It's a benchmark data set for classification tasks. Now, a little technical details, and this has to do with the features. The inputs are grayscale images, 28 by 28 pixels, and the training set here is 60,000 images. What does it mean, 28 by 28? So, images have two dimensions, one and another, right? Okay, now, there are dots or little cells within that image that store some information. Yes? The 28 here means that you have 28 of these intensity values on that direction and 28 in that direction. Okay? Now, each of those values is a number between 0 and 255. And now, each of the values between 0 and 255, they tell you how gray the pixel becomes. Okay? Here we are. This is how we start coding this. The goal is that we would like to actually get the input, get a hidden layer, one, an output layer, and then get the probability. So the arrows actually denote all of those parameters, the W's, for the first input to the hidden, and then from the hidden to the output. And computationally, we are so lucky that we have something called now TensorFlow. TensorFlow is like a high-level API library within Python that people have implemented all of those nice things within, and we are able now to actually just extract a couple of those things, call them, and make predictions and so on. All right? Now, is TensorFlow the only thing that exists? No. We are using now TensorFlow for just educational purposes, but there are also other tools available that contain all of those nice functions, libraries, and so on, sub-libraries, and so on. PyTorch, for instance, you may have here. Very good when you are working with LLMs, for instance. Now, from TensorFlow, what we do is that we need to import a couple of tools. Keras is one of that, and from Keras we have to actually get the layers. So the layers is actually what it stands for, layers. So it will enable you to just write 2 lines of code and set up your architecture. All right? And that's what we are doing there. We are defining our model. You see, model equal from Keras, make a sequential network with 2 layers. Layer 1, which is a dense layer, everything is connected to everything else. A number, comma, the activation function. Now, can you tell me what 512 is?
The number of nodes.
Or what denotes? Yes.
Number of nodes.
Say, I don't hear.
Nodes.
No.
Nodes.
Yes, my question is, we have parenthesis 512, comma, activation. What does 512 denote?
Yes. The number of neurons in the
Neurons.
layer.
That's all.
Very good. So we have a layer, layer number 1. That is actually, the 512 means that I want 512 neurons within layer number 1, within the hidden layer. Okay.
No, just I wanted to ask, so is this a hidden layer or this is an input layer? So what do you think?
An input layer.
Because the layer may
It's the
be
first.
10 neurons.
Do we have activation function in input layers?
No. Even layers do not have activation.
It is a hidden layer.
It's a hidden layer, yeah?
The hidden layer. Very
It's
good.
not an
The
input layer.
other is the output because it has 10 categories.
We'll go to it.
Yes.
We.
Yes.
Activation, the ReLU. Remember we said that the popular activation function for a hidden layer is the ReLU. Here we are. Now, the output layer is a 1 with 10, comma, activation softmax. Why 10?
Why 10? How many classes do we have? So we want to classify these images to 10 classes, 0 to 9. So that's why.
Very good. 10 classes, so that's why we have the 10. Okay? Why softmax?
Why not ReLU?
If it's negative, it's 0. Because the probability is from 0 to 1. Because the probability is from 0 to 1. So the softmax is a good activation function to measure the probability to be one of the output. For example, to be 0, 1, or 4. Yes.
Remember we mentioned with the softmax is actually the activation function that outputs a value between 0 and 1, anything in between. Right. It outputs probability values, okay? So that will actually give a probability value to each of the neurons that corresponds to each of the labels. Good?
What does the word sequential mean? Keras dot sequential.
Right, very good. So the sequential actually means that as I'm writing, we're writing there, stacks the layers linearly, okay, to create a data processing pipeline, linearly, okay? So this is what you traditionally will use, the sequential.
I have a question.
Yes.
Most of the related.
About hidden layer. What the number does it need to be 5, 12?
Why?
Why it doesn't be 6, 12, for example?
Very good. Very good point. So those numbers, the number of neurons and the number of layers, remember we said that these are hyperparameters. These are parameters decided by the user. And that means that in order to decide in the right way, I have to do something hyperparameter tuning. What does this mean? It means that I start with 32 number of neurons. I test, I train my model, I get an accuracy. Then I go back, I increase, I make it 64. I train my model, I get an accuracy. Then I do that again, train it, get an accuracy. And the number of neurons that will give me the highest accuracy will be the winner for the final network. Okay? Now, I oversimplified what I just said, but this is what is happening. We are doing hyperparameter tuning. We are actually cherry picking the number of neurons and the number of layers. And not only this, we have the activation functions and a couple more things that we have to cherry pick. Okay?
Just remember that dense means fully connected. So every neuron is connected because you see later on the dropout layers and things like that, and they are fully connected.
All right, we explained that pretty well. And now we are ready to go to the next step, which is getting everything together. So you define the model, you define your architecture. Okay, but now you need to actually decide about 3 things. One is the type of optimizer that you would like to use. 2 is the type of loss function that you would like to use. And it's the type of metric that you would like to use in order to monitor the behavior of your training phase. Okay, so we start with the optimizer. Remember that we said once we set up the architecture and we have all the parameters that we would like to train, then we start feeding training data, and then there is something called backpropagation that is happening, right? But then we said that at the heart of backpropagation there is something called gradient descent. All your parameters are located in this complicated surface, and your goal is to actually identify steps within that surface that will move you away and take you to something called the local minimum on that surface. And at the time that you reach this local minimum, the algorithm terminates, you receive the thetas, you give it to the network, and the network gives you predictions. Yes? Okay, now, the optimizers, we have many choices, and are actually the ones responsible for taking you from any arbitrary point on that surface and taking you to the loss function. So gradient descent is the general term for that. So for gradient descent, which is a line search method, there are a lot of different variations or different algorithms that you can use in order to optimize differently. So for example, gradient descent, after that, there is something called stochastic gradient descent. After that, it's called something mini-batch gradient descent. This has to do with how much of data do you give to the gradient descent algorithm and how the algorithm actually moves on this complicated surface. Okay? Now, though there is a lot of issues with those algorithms when you are dealing with real-world applications, and these have to do with overfitting, for example, or the vanishing exploiting problem. Okay? What people thought is that, okay, we need to actually find a way to improve. And they came up with different optimization strategies, different optimization algorithms for solving these issues. Okay? Another very popular issue when you are dealing with optimization is getting stuck in a point that is neither a local minimum, neither a local maximum. It's called a saddle point. Okay? So that can happen. So people thought about it and they said, okay, how can we avoid that situation? And they came up with something called momentum. We are not going to go through momentum, but it's something for you to think and store it in your memory, so you will see it in your future. Momentum is a way to actually push away from those anomalies in that surface and take you to the right place where you will identify a local minimum. Okay? After this, a lot of other algorithms, like the RMS probe, came up that is actually improving the optimization strategies of the learning phase in your model. Okay? Any questions? Yes.
Why did you use Adam for optimizer?
Very good. Adam is another variation. Okay? I didn't use Adam here just because I wanted to put RMS probe. Huh?
Just for example.
This is just for educational purposes. That's why I didn't use. Do you have an answer for what you asked? I do have for you. So remember that the choice of the optimizer is also a parameter at the end of the day, and it's a hyperparameter at the end of the day. Okay, you can tune it if you want. I mean, I wouldn't recommend you tuning this parameter, but it's a parameter selected by the user, and it's actually a sophisticated user that goes very good, that has a very good sense of optimization, numerical optimization, can actually select the right one. Okay? I have one more comment on this, on the optimizer. Have you actually wondered ever, when you are taking your data, giving it to a model, and then you are saying click fit, and then you are waiting to see the output? Have you ever wondered why it's taking so long? One of the reasons could be that it takes you so long to converge and get a solution. It has to do with the optimizers. There are, in the literature, there are something called fast optimizers. Optimizers that take you from a random point in a surface very quickly to your local minimum versus others that take very slow to go to the local minimum. Okay? That is actually one of the reasons why when you hit click and you feed the data, it takes a lot of time to converge. What we say, when you are actually reaching to a local minimum, then we say, oh, we converged. Okay? The choice of the optimizer is crucial for that. How fast you will reach. Okay? I recommend, if you haven't taken a numerical optimization course, you will see even much more sophisticated numerical optimization strategies. For instance, second order optimization techniques, simplex methods, and so on and so forth, that can be directly also applied to neural networks. Okay? Now, the loss. The loss, we said previously that, okay, what can I take? Y minus y hat. Squared it, sum of it, and that's my loss, right? Is that the only one? No. So there are different losses depending on the task that you are trying to solve. So if I do y minus y hat squared, and I have 0 and 1, that is a little weird, isn't it? In a regression problem, that is actually the loss function, y minus y hat squared. But when I'm doing classification, that's not the one. What is going to give me, either 0 or 1? That's why sparse categorical cross entropy is one choice that you can do when you have actually a classification task. I leave it to you to discover even more. This is not just the one. There are much more than this. Okay?
Is it better to do a composite loss function or just to choose one task?
It depends on your task, what you are trying to do. So, for example, this is a very basic classification task.
So it would be better to choose one of them.
Exactly. Yes. This is actually very basic. But if you are doing actually something called segmentation, okay, you may want to choose a different loss function. Segmentation, you are still doing classification, but it's pixel by pixel, not whole images by whole images, okay? So it really depends on the task. The good news is that TensorFlow has the documentation, so you can go in and check one of those. So it's a description, one line for each, okay? And then the metrics. So while my algorithm is training, I want to monitor its behavior. I want to actually see whether or not we are improving by every other epoch. Okay, and within even epoch, we would like to actually see whether my accuracy is getting up. Okay, that's why I'm picking metrics equal accuracy over there, just to see whether or not we are doing a good job. Okay, it's also very important to save all of this, because when at the end of the day, once you have the accuracy for each of the iterations and for each of the epochs, you will be able to actually visualize those learning curves. And with that, you will be able to actually inspect whether you have overfitting or not. Okay, so just keep that in mind. It's important for the accuracy element. Questions? Okay, so here is the normalization. Remember we said normalizing is important. What we do is that each of those pixels has a value, 0 to 255. But as I said, the distance between 0 and 255 can actually magnify over the network. And especially if the network becomes deep and deep and deep, then this difference will actually explode eventually. So it's not good for training to have such big differences between values within the network. And therefore, what we just do, which is something very simple, is that we are taking and dividing all the pixels for this 28 by 28 image by 255, by the maximum value. That will take you to a range. Each pixel now will have a value between 0 and 1. Okay? That's the normalization. This actually will stabilize training. This helps backpropagation.
This is data pre-processing. So we are pre-processing our data before we feed into our model, the data itself.
And you know what? Mathematically, this doesn't have any value. No one is telling you mathematically that the backpropagation needs to have something normalized. This is coming more from a technical point of view. Okay? Now, what Gerta mentioned previously, it's actually we see that again. Initialization, prediction, measure, optimize, initialize. That's the cycle of my training. Okay? Then we say repeat every 5 epochs. So that means that we have to actually give to the model 5 times the full data. So the model needs to see the data 5 times. The full data. Okay? 5 times. We start with initialize. Random weights. So what does it mean? Random weights means we are on that surface. Remember this complicated one that has many local minima and so on. And we say, close your eyes, pick a point, and from that point we're going to start. That point has actually a set of weights, theta 1 through theta 1 million. Okay? Now, this is your starting point. You give it to your network, you give an input data point, and the network is making a prediction. Guess what? The prediction will be completely off. Right? It makes sense, because if you close your eyes and you are somewhere there, the probability that you're going to be at the local minimum in that surface is 0. Everybody can guarantee it. So we make a prediction, and the prediction is wrong. What happens? From that prediction, we need to actually adjust the weights. So we need to go backwards in the network. Adjust the weights, update the weights, and then feed the input data again and make another prediction. Okay? So the orange box is what I said go back. is what I said, adjust the weights. Is actually doing what? You are on the surface, now from that point that you randomly selected, you are just moving down a little bit. Okay? When you are moving down a little bit, that means actually that you have applied or that you move towards the direction of the negative gradient. Okay? Remember this function, we have to go that way in order to find the local minimum. Same thing there. The negative gradient will tell you that, okay, you have to go down. Now, this process repeats, the weights get better and better and better, and then they stop. We got the best because we are minimizing our cost function, which is the error. Once we minimize our cost function, we can start now using that model with the associated weights to make predictions using unseen data. Good? Excellent. Okay, now this is from a the practical implementation. We have our training data, we feed it to the model that we have developed or we have designed, and then we start. The model is running, it trains, and you see now here different parameters. One is the epochs. The epochs, we said, it's the number of times the model sees the data. Batch size, make a guess, what is it?
The number of images per iteration.
Say that again.
The number of images per iteration.
Okay, the number of images. So,
A sample from the...
very good, I like that more. A sample from that, right? So, remember that the training data could be, let's say, 1,000. Would you give the full load of that training data to the algorithm to update the weights? No. Why is
We
that?
have to put away some data to validate or
No.
to test.
No.
Yes, but
Hold on.
training, we have to choose only part of them because other data.
Hold on, that's not the case.
No, we'll use all of them, but just in batch.
Yes, so
Not
in
part
the
of-
training,
Yes, the training only is some of them. For example, 80% of them.
no, that's different. This is the splitting between training, testing, validation. But I'm not asking this. I'm asking something else.
So which side?
We have 1,000 training data,
Yes.
okay? Would you take all of the 1,000 training data, we already did the splitting. Would you use the 1,000 training data and give it to the model immediately? You wanna?
I wanted to answer the part that first you split the whole data set in a training section that you use to train, and the other part to make predictions about it.
Okay, we are done with this.
Yeah.
We are done with this, right? And again, now I have 1,000 training points that I already made, okay, just for training. Would I give this 1,000 directly to my model?
Why not?
Huh?
Why not? We can give it all.
We can give it all. Mathematically,
It would be-
very good. Actually, that's the answer.
It would be
Mathematically,
computational.
why not? We can give it all. That's
I
the training
think,
data, right?
I
There is a
think-
computational issue.
I think it would
Memory.
be
So we can delete that batch size equal to 128 and we can still run that model code fit. Yeah, and it will work, let's say, but
It works.
now, yeah,
It
has
works.
some disadvantages.
Gradient descent will work.
Yeah.
It will take forever.
Yeah.
Memory is an issue here. You cannot take the whole training data set and give it. 1,000 was a simple number. We're talking about millions training points. So you cannot just give it to your model and say, okay, use this big batch of training points and update the weights. It may even affect the gradient descent at some point. Again, mathematically, that's not the case, but from a memory perspective, this is the case. So what we are actually doing, we are saying from this 1,000 training points, get 188
28.
samples. Okay? Give it. Go through, update. Then get another 128. Yeah? Then get another 128 until we reach all 1,000.
But this is one epoch.
But this is happening within one epoch. Now, next epoch, again the same story
Yes.
starts. Okay? Good. So there is something important here. The batch size is the one that actually helps you to speed up. From a gradient descent perspective, it has been proven mathematically, it has been proven that even taking one sample, not 128, but one sample at a time, will give you the local minimum. Mathematical guarantee. That means that someone sit down with a pencil and prove it. Okay? So this is called stochastic gradient descent. Okay? That is called mini-batch gradient descent. Stochastic gradient descent, again, mathematically has been proven with probability equal 1 that you will converge to the true local minimum. Okay? Even taking one sample at a time. So what's the difference between taking all data versus one sample versus 128 is the trajectory that you're gonna see on the surface. If you take all data, the trajectory will be smooth and it will take you to the local minimum. If you go one by one, you will feel that you are actually a drunk man on that surface going here and there, simply because you are just taking one sample at a time. If you are taking 128 or higher, that means actually you are smoothening this trajectory on that surface. Great, good. Okay, watching the machine work, that's what we are actually seeing. Gerta showed that previously. There is the loss, then there is the accuracy. These are the two curves as a function of epochs. So the accuracy needs to go high, okay, but the loss needs to go down. All right? And once we have the trained model, now we can go to the test images. Since we have the split, take the test digits, use the function predict. What happens there is that we're taking the test digits and we give them to the network as an input, and the network does a forward pass and gives you just a prediction. Okay? And you print the predictions. So what you're gonna see there is an array of numbers that will tell you that the highest probability is at the location 7. Okay? And that will correspond to the digit number 7, and you're done. Okay, so I'll skip this. The key terminology that I want us to just keep in mind here is that tensors are important to, I'm not talking tensors from a mathematical perspective, but tensors as a way how to, not store, but how to represent the data. So when we are talking about images, we are talking about 28 by 28, two-dimensional arrays. Okay, but now, is this the case? Always, no. Real-world scenarios, we are not having just 2 dimensions in the data. We have more than 2. When we have videos, or when we have a sequence of images, when we have grayscale versus colored images. Colored images have 3 channels, R, G, B, red, green, and blue. So an image can be represented in 3 different channels. This is actually increasing the dimension. So it takes you away from 28 by 28, it makes you 28 by 28 by 3. Okay? When you are going to videos, then you are adding another dimension, the time. Because you have multiple images by color, by time. Okay? Dense layer, we know what it is. Activation, we know what it is. Overfitting is the key. Okay? We discussed this a lot today. We said that overfitting happens. Remember, the more complex you make your model, you may end up with overfitting. Okay? Simply because you are learning the noise and not the useful information from the data. And not only the useful information from the data. You learn everything from the data. Learning noise from the data can lead to overfitting. You won't be able to generalize to unseen data. Good?
If you can mention how you discover overfitting, let's say.
Yes. Remember that I had those curves here? Overfitting, we can actually see if we plot one more curve. So let's pick accuracy, right? And this is the training curve, the training accuracy, just using the training accuracy. But when we are working with deep learning models, when you have your training data, you are using also a small portion that's called the validation data. Okay? Now, you are using the validation data within training to actually see the performance. Okay? Now, you can plot both curves at the same time. And you will have the accuracy on the top, and the training accuracy on the top, and the validation accuracy below, right? Now, we can identify if there is overfitting, if there is a big gap between the training and the validation loss. If there is a big gap as a function of epochs, that means that, okay, that is an indicator of overfitting. We need to do something. And then we start doing something, which is called early stopping, drop out, and so on. Good? All right. Why don't we start the coding then? We have time.
We have 30 minutes.
30 minutes, or plenty of time.
So we'll be around.
You want to ask something? Yes. Yeah.
So when we do the epochs, it's important to keep timing, but for them, when we analyze the data,
The milliseconds is very useful there.
is it important to keep the timing that they run or no?
Yeah, why not? It comes for free.
Yeah. It's not that you specify, it's the output coming from the language that you're using. So sometimes we just want to check if there is something in the bottom of the system. We can focus on doing some evaluation on this. We check the methods evaluation.
Yeah. You can use Google Colab. I don't use Google Colab right now. I'm using my own machine for that. Okay? And we're gonna build our first neural network. Actually, we're gonna see what we saw in action right now. And you're gonna see it in your machines. We get 70,000 handwritten, the MNIST data set, in other words. And we're gonna set up everything the way we did before, and we'll see the output. Okay? I'll give you 5 minutes to set up, and then we start. Should they compile those? Should they run those? What you did? Okay. I think I have all that. Yeah. I'll start to allow the. Or actually, it's okay, let's do the Yeah. Yeah, well, I'm like, yeah, no. I didn't use the name. Yeah. I think we do. I don't know. Okay. Any questions on the setup? Oh, okay. That's the worst case.
No questions, it's just a problem.
Okay. Yes. Yeah, so there I will tell you do not wait because so Okay, so I'm gonna talk, I mean, there are the libraries, the TensorFlow, that I'm loading initially, and NumPy, which is actually the library for the data. For dealing with matrices, arrays, and stuff like that. But I want to talk about the part 2, which is checking the GPU. And again, don't look at the code as is. It doesn't really matter. But what it matters is the idea behind GPU versus CPU. Most likely, I mean, in my machine here, this one, it's a very simple machine, okay, cheap one. That is actually providing CPU power for me. So it's not compatible with the TensorFlow GPU program. So CPU means that you have 4 workers, and those 4 workers will work to execute something for you. Again, I'm oversimplifying right now the discussion, but this is what is happening. Now with GPU, things get better. So if you have a graphics card in your machine, then you have not just 4, but you have 800 workers that can actually work together, communicate, and execute something for you. Okay? However, that means that you have to buy a graphics card from NVIDIA, install it in your machine, and then make it compatible with blah blah blah, with the TensorFlow. It's not a big deal, it's easy to do, as long as you are willing to pay a little bit to get a GPU card. Okay? But that's why we have Google Colab. Google Colab, if you have a Gmail account, they give you access to GPU. It's called, I saw T4, right? T4 GPU. So if you change the runtime, there you can just go to the T4 GPU, and you can enable it for the notebook that you are working on. And all the computations that will happen will go to the GPU, and they will execute. Don't do it today because there is no need to do it today. There is no need to use the GPU today. If you do it, you may end up tomorrow, Google will block you and will tell you, oh, you have to pay a little bit extra to get access again. Okay, so just leave it as a CPU for today. It's not a big deal. You can do it even in your local machine. This notebook is very easy. If you did it, that's fine. No, if you did it, done. There is no way back. But probably they won't lock you out, so don't worry. I'm just saying because that happened to me. Okay, so that's all about that. The loading the data set. So Ogerta mentioned something important, and I completely forgot to mention. Remember, when we are doing with training, right? So we have training, testing, validation, right? And that means we have a function that does the splitting for you. Train, test, split, okay? Within scikit-learn. That is actually sampling the whole data set in a sophisticated way and comes up with a training set, testing, and a validation set. Now, what I do here is I'm just using the Keras data set and load it, and they already have a mechanism behind when I'm loading and give me a training set and a testing set, okay? So I didn't do it the complicated way, but I just do it the easy way. The training images will be used for training, the test images will be used for testing. The labels, training and testing, will be used accordingly too, right?
How many data sets do we have here? So we are not splitting as we mentioned, so usually what happens, we have a full data set and we have to split it into training, validation, and testing, and so on. In here we are just loading, we're using the load data function that it comes with Keras data set method into it. So just a question for you is how many data sets we have after we run this load data method?
70%.
You are saying 2, how many do we have? No, we are not doing any split, we are loading it. So we have just a load data method in here, and then we are executing it, and what the method is returning, let's say. So how many data sets? You see that on the left side. How many do we have?
Do you have two or four? So this is a question. So just we have a train images data set and we have a test images data set. We have a train labels, we have the test labels. So how many total?
We have two data sets, one for training and one for testing.
And two for the labels.
And for the labels, what the labels are labels data sets?
Yes.
Yes.
It depends on how you count.
How many
Four,
do you
but
have? Four. Okay.
it depends on the definition.
Uh,
What is the definition
We
of
have
that
tuple
data set?
and another tuple. The first tuple is the first data set, which is for training. The second one is for testing. But the
Images
data
and
set,
training are the same, I think, because it was the labels, 10 labels from 0 to 9. This is. But the number is the same. Train images and train labels as the number are the same, but labels only 10 of them. Okay, and you can also have a look at the part 4 of the code where we are exploring the shape of our training and testing data. So you see in the first one we have a linking of the shape of our train images and the train labels.
60,000.
So you see only for the training we have two different data sets. Yeah? And you have to see the shape of the data set.
Sorry, but what is the definition of that data set? What is the definition of data set?
The data itself, the data. We don't have one data. 60,000, the same. Labels and training. The first, then, let's see. We can see that the previous discuss and understand the job. It's not just to run the code, it goes in 10 seconds that everyone can run it and get it out. You have to understand it. It's important to explore and to understand what data we have. So why the first one, the train image is shaped with 60,028, and the other one, the labels ones, contains only 6,000. 60,000. Yeah, 60,000. Because in the first we have the image, right-handed. Yes, and the other is the number 0, 1, 2. These are the labels. Or if we have the outputs of marks, we have only probabilities. For each of the corresponding image that we have in the training images data set, we have a corresponding list. Is it a 0, it is a 1, it is a 2, and so on. And that's why. Yeah. 60,000. But for the shapes, we are labeling. We are not labeling at all. They are labeled. We are just loading images. We are not doing labeling. Yes.
So if you just plot one random instance, one random observation, you see here, for example, its corresponding label, and then you see the grayscale image 28 by 28, which is the digit number 5. Okay? This is the training data that we're gonna load, or we're gonna give it to the neural network once we set it up and get the parameters and then have the network ready.
How many images do we have? In total, how many images do we have? Can I get it from 60,000? 60,000 images. Yes. Yeah? Yeah, yes. Yes. Okay, 60,000.
Okay. Pre-processing the data. Pre-processing the data means that we have to divide by 255. Remember, each pixel is a value between 0 and 255. We divide by 255 to make the values between 0 and 1, right? So, again, it's nothing special here. It's just the syntax. the float 32 divided by 255, you get a good precision. And then it's actually when we set up the network. It's the time when we actually need to get our model, right? So we said sequential will be the key here. And we have a dense layer of 128 and an output layer of 10. We already know that. What is the first layer? There. It says layers dot flatten.
Pixels of the input images.
Yes, but what does flatten mean?
From 2-dimensional to 1-dimensional array.
Okay, so what that really mean, remember, a neural network sees the basic, the traditional neural network has its neurons, right? Each neuron will be what? 1 pixel. Yes? Is it safe to say that the features for my data are pixel values?
Yes.
Yes? 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 Yes. The features for my data set are pixel values. Is this like a good, this is actually the motivation for tomorrow. Is this a good actually way of thinking when we are dealing with images?
No, maybe because images have colored.
I can flatten the color too. I can flatten, if we have color, that's a good point. If we have colored images, 28 by 28 in a red, 28 by 28 in a green, 28, I can flatten each and then put them all together.
I don't think it's not.
Say that again.
You rely on pixels and you don't
I rely on pixels. That actually is very powerful as a statement. I rely on pixels means that I'm very isolated. Okay, so I can give you a hint here. When you rely on a single pixel, do you know what your neighbor is?
No.
Okay, that's the motivation for CNNs. You need to actually know how your neighbors look at you and how you look at your neighbors. That's why now we actually have to go through windows and create features. Okay? Now, another way of why this is not the best way of coming up with features is actually the number of parameters that we're going to generate. So if we start with 700 something input features, and then we go to a next layer which is 128 neurons, and then we go to another layer of 128 or 64, that is going to actually explode the number of parameters. Would that be good for training? No, we want something smaller. So this is another motivation of why we're going to use what we call convolutions, to reduce the dimension of the parameters. Okay, we will see that in the demonstration tomorrow, but that's the idea. Okay, clear why softmax? Yes? Is it clear why we use the softmax again? Yes?
Just on part 6, you see that we are building the neural network, but if you run a piece of code, you don't see any output at all, because it just has built, but we didn't compile and mistakes in order to start the training and so on. We have just built it. Okay, no output if you run a piece of code.
All right, now it's the time where we take everything together, compiling. Okay, so remember I used RMS prop previously, but now I'm using Adam, the Adam optimizer. You can do gradient descent if you want, so has gradient descent. The loss is what it is, and the metric is what we need to actually monitor. And when you compile again, or if you run this piece of code, you won't get anything out. But when you run this code, you will get. It's time where you're going to fit the data into the model that you have compiled, and the model starts learning the parameters. Or actually, the algorithm helps you to learn the parameters of the model. And we said we want the batch size, we want the number of epochs, and now there is also one more thing there that is called the validation split. Okay? remember, within training data, we are splitting, we are getting out another portion. That is the validation. All right? So we are specifying this as 0.1, 10% of it, we want them to be validation. Why do we do that? To plot the learning curves and see whether or not I have an overfitting issue. Good? Now, the rest is fine. Batch 32, you can do 64. I would say 32 is fine here. The number of epochs equal 5, that's, don't make it more than this. Just keep it simple.
Something important in the outcomes is that, as you see, the accuracy from one epoch to another is going to be increased. So in the first epoch we have 0.98, and in the second one we achieve a gain of 0.99. And when it comes to the value loss, it will be decreased. So this is evident, and it makes sense.
Makes sense why that's happening? Yeah, right? Validation is actually the unseen data within the training stage. So you update the parameters, you have a model, you train it, you test it with the validation. And that's why you are getting lower accuracy. Now, you would imagine that as I'm increasing the number of epochs, then I would improve and I'll become better and better and better, okay? Now, I already reached the highest there, so with this data set, we are good to go. 97 plus accuracy, right? Okay. Now, we evaluate the model and we're getting slightly lower. And
Sometimes can you go a bit up?
Up.
So it's something that we have to make sure to understand about when we evaluate the model. The accuracy that we achieve is 0.97%. Let's say. When we train the model, the accuracy was what it was the highest in epoch 5. So 99.5. You see there is a difference between the accuracy that we achieve in the training and the accuracy that we achieve when we test it, training and testing accuracy. This is different because on part 9, we're evaluating the model with the part of the data testing that the model has not seen. And this is the accuracy that we report how good the model is. Okay?
Good. This is actually when we are plotting the training and validation accuracy. This is what indicates overfitting, not in this case. You see the difference between 0.98 and 0.97 is so small, right? And as you increase the number of epochs, I mean, this difference increases, but it's, again, not significant. So we are okay, I would say, with what we have. When I'm making predictions here, we are actually predicting the correct digit. So there is a little code to get the label of the prediction. But this is what I want to discuss now, briefly. Actually, not this is the challenge. So, I want you to go and change from 128 to 256 and see what is happening. So, you need to go to the layer, challenge 1. You need to go to the layer and change the 128 to 256 and see what you get. Go slower, right? Yes. Makes sense why it goes slower? More neurons, more parameters, slower. Okay? The model is more complex, in other words. Let me see how small, how small. Ah. Done? All the... I'm more interested in the overfitting, to be honest. You know, you see that we, at some point, we don't care much about the accuracy. So, does 98 versus 97 or 99 versus 97 make a difference in that task? No, right? Would that affect? No. But is overfitting evidence now? I don't know, I'm asking.
Yes, in the fourth epoch it went up and it went a little down and up again.
Okay.
So it was not linearly getting more accurate.
So, to actually get more evidence that there is overfitting, you can increase the number of inputs. You can make them, instead of 5, you can make them 15, 20. Then you will see something. But don't do it. I just say, don't kill your machine. It takes time and then it's going to kill your machine. Right?
Yeah. But you can play now with the code.
But now, I mean, that is actually the nice thing from today. So you don't really have to do everything. You really know now that what to do. I mean, I said overfitting and you already know that, okay, I can increase the number of parameters and I can see overfitting. Do you believe it? Yes, you do believe it. You understand why. Do I really have to try this out? No, you don't have to really try this out. It's waste of energy. Waste of effort plus energy, right? So from now on, that's the idea, that we're going to start having a better instinct of what to do, how to approach things. Okay, let's go to challenge number 2, which I said change it from 5 to 10, okay, and see what is happening. Then the curves will start showing up some type of overfitting, all right?
We should leave the number of neurons to 156.
You can leave the number of neurons to 256, but don't run it. Yeah, unless you really want to.
No, I don't know.
Okay, then don't do it.
Just ask me.
Challenge number 4 is what I want us to discuss, or is what I want you to discover. Remove normalization. Do you remember that we had actually a piece of code that was divided by 255? Okay, get rid of it and rerun the whole node with 5 epochs and 128. Don't go to 10 and 256, but remove the normalization. What do you see? Working? No? Huh? Oh, okay. Oh, it's running. Yeah, I'm good. I thought it got stuck somewhere. I mean, you don't have to submit info, so don't worry if you don't run. You can click cancel. With TensorFlow, so there is a little setup. Okay, are you using ChatGPT? Okay, so what you can do, you know the specs of your machine. So go and find out the specs of your machine. So model, So go to system and then run it. So take this one and then give it to ChatGPT and ask, okay, I'm using the notebook. I'm using the Google Lab. Do you have Jupyter notebook installed in your machine? Okay. Do you have Python? Okay. Okay, so did you remove normalization?
Yes.
Yeah. What did you observe?
Accuracy increase or decrease? Went down.
Down? A good amount. Right?
Not a good amount.
Not a good amount? Okay.
0.0.
Yeah.
Okay.
It was 99.8 and it went to 97 point something.
Okay, so yeah.
It decreased but not significant.
Very good.
Yeah.
All right, so you realize now that normalization is important.
Yes.
Okay. Now, this application, it doesn't actually highlight this problem, but if you go to more sophisticated, like what we're gonna do soon, tomorrow, you will see that every single step matters. If you don't do normalization versus you do normalization, if you use this specific cost function or activation function versus another one, if you do max pooling and if you don't do max pooling comes tomorrow. That matters, okay? We will see why. I think that's all at 6, right? We finish at 6?
Yes.
We are on time.
We are on time. Okay, so hope to see you all tomorrow again. And we're gonna stay a little bit here for more questions. I'm coming.